Okay, we're continuing on here. Chapter 14, I think. Yeah, that sounds good. And chapter 14 is pretty much all the leftover organicness that is left. So we started talking about last time really carboxylic acids, I think. And carboxylic acids have a functional group of carbon oxygen double bonds, so a carbonyl group and the OH group. So that is basically your functional group for carboxylic acid. Again, sometimes in formulas abbreviated as COOH, and that is basically that carboxylate group there. And that's what that abbreviation means. It is going to always be the functional group. It's always going to be at the end of a molecule. Again, because we do have, for example, here we have the hydrogen there. And just like we have sort of with our aldehyde, like we talked about, it does need to be at the end of a molecule. Otherwise, the hydrogen will have too many bonds. So we do name it based off of how many carbons there are. So in this case, there's 2 carbons. This is what is known as ethane. And then we drop the E and put oic acid at the end of it. So this is ethanoic acid. Again, we do not need to give the location of where the carbonyl carbon is, where that carbon oxygen double bond is. Again, because that really always should, in this case, be position number 1. So we don't need to give it in the name, but we do need to use it as carbon number 1 if there are some other groups attached. So if there's some other groups attached, you would always start numbering from that carbon as number 1, and obviously give the locations like normal of all the other groups. We could also see this on a benzene ring. And again, remember that when it's sort of on the benzene ring, it will be sort of attached to it, even though it's sort of part of it as well. And again, instead of benzene, this is going to be benzoic acid. So same idea here, wherever the functional group is attached on the ring will be carbon number 1 if you had to name any other groups that are attached. Because it is a carboxylic acid, it pretty much will do an acid reaction. It can do an acid reaction, for example, with water. And it could do basically a Bronsted-Lowry sort of deal. It's going to donate its H plus over here to the water, which would act as the base. The result of that there, you'll end up with something like this, which is acetate basically. And you'll make H3O plus. So it can do definitely just a basic acid base reaction. In addition, it also is one of the few things, as we talked about, I think towards the end last time, that really can beat sort of an alcohol in terms of boiling points and melting points. And that's because it really has 2 sort of polar groups. It's got this OH, which is definitely a polar group, and it's got the carbonyl group, which is a polar group. This allows for it to basically hydrogen bond in a couple of places. And when it hydrogen bonds with itself, it will hydrogen bond in a couple of places. Again, hydrogen bonding being a relatively strong sort of intermolecular force. And because of that, it will actually have a pretty high boiling point and melting point because it's going to take a lot more energy to sort of separate those guys out. Any questions on that there? All right, so let's take a look at this one here. We want to write the balance equation for dissociation of butanoic acid in water. So let's just start with butanoic acid, right? We're going to draw it, so we're going to go backwards. So butane basically tells us 4 carbons. And oic acid tells us it's a carboxylic acid, which once again, you could put on either side. I'll just put mine over here on the right. And like normal, everybody else here is going to be hydrogens to get everybody to 4. So there's butanoic acid plus our water. This again is going to be really just like a Bronsted-Lowry type of deal. It's going to donate over its H plus. That is going to give us pretty much this entire thing without the H, basically. And that's going to give us CH3, CH2, CH2, C double bonded O and O. What's going to happen with the charge, much like we talked about with Bronsted-Lowry conjugate acid base pairs, it's not just a hydrogen, but the plus affects the charge here. So that acetic acid was neutral to begin with. It will then become one more negative in this case. It's actually at that oxygen where that occurs. And our water will gain the H and the plus and become H3O plus. Any questions on that one there? Oops. I hope it. All right. Now, because they're also an acid, they can really react with a base, a real base. I guess water is a base, but a true strong base or something like that. And it really will do basically an acid base reaction like we talked about with when we're doing acid and bases. Whenever you take an acid and a base, you get water, and the same thing is going to happen here. We're going to take the H from the acid, and we're going to take the OH here from our strong base to make the water. So that is where water comes from. The result of that is pretty much this is going to stay the same. As you can see there on the right-hand side, nothing really changes, but it does gain a negative charge here. Again, because it really, in this case, lost an H plus, not just a hydrogen. When we get rid of the OH from the sodium, that leaves us an Na plus, and it will make what is referred to as a salt. And a salt, like we've talked about before, is just an ionic compound. And that's what we got going here. And you don't have to worry about naming the salt, but that is basically the reaction here that a carboxylic acid can do, just a regular old carboxylic acid in a strong base will do an acid base neutralization reaction, forming water in this particular case. Any questions on that there? We're not going to name the acid salts, so you don't have to worry about naming them. So we'll skip that there. But carboxylic acid salts are typically ionic compounds that have strong attractive forces. They are typically solids at room temperature. They have high melting points and are usually really soluble in water because, frankly, they're a salt like any other salt. The salts typically are very soluble in water. They typically break apart into ions in water. And that's essentially what's happening here. When that sodium benzoate, for example, goes into water, it's going to break apart. That sodium is going to float away, and the other guy is going to float away. And the same thing with all these guys here. A little MSG over here, a little monosodium glutamate. And again, same idea. It's going to break apart. And these guys are going to basically break apart into the positive ion and the negative ion. Carboxylic acids are used as preservatives, flavor enhancers. Again, sodium benzoate inhibits growth of mold and bacteria, and sometimes added to fruit juices and margarines, relishes, salads, and jams. MSG, sometimes added to meat, fish, and vegetables to enhance flavors. So why don't you take a second here and write this reaction. It's good practice drawing the propanoic acid. Why don't you draw the propanoic acid and see what you get at the end there. Okay, so we'll start here. We got propanoic acid. Again, the oic acid tells us carboxylic acid. The propane part tells us it's 3 carbons, so 1, 2, and 3. We could put our carboxylic acid group on either end. So I'll go to the right. And that is, again, our propanoic acid. We're going to react this with sodium hydroxide. So this is going to be, again, really just an acid-base reaction. So always in this sort of situation, OH from the base, and it's always that H there that's attached to the oxygen from the acid. That is going to come together to make our water. And really, whatever's left over is what we got going on. Remember, though, that the charge does change, so it will become negatively charged. And when that guy is released, it is a positive sodium that goes with it. That technically makes the salt, those two guys together. And that's what you end up with there. Any questions on that there? Yeah. Would you have to give both of these? Yeah, I would say you probably should in this particular case. Definitely should hopefully see this, but water would be good with it as well in this case. Yeah. Yeah. You could if you want to more of a condensed-ish type deal. It could be something like this. Something like that if you want. Actually put it together. I guess put the sodium on the front of that too, if you wanted to. Yeah. Other questions? There we go. They agree, so that's good. All right. So carboxylic acids are also part of the metabolic process within our cells. During glycolysis, molecules of glucose are broken down into pyruvate and pyruvic acid. And again, this is what we see here. We got basically our reduction occurring here and taking kind of like our ketone back into basically like an alcohol in this case there in a sense. And we form our OH group there. Kind of the same idea we talked about with ketones or aldehydes. We're basically putting an H onto here and an H onto there, making that then into a single bond is essentially what's happening. In the Krebs cycle, also we see a lot of this happen. We have a lot of carboxylic acids there, citric acid, and these guys get transformed along the way to produce some CO2 at the start of the citric acid cycle as well. And obviously being oxidized or reduced depending on which way you're going gives you some different stuff throughout that sort of citric acid cycle. Let's then talk about esters. Esters, another organic group, and esters are really a combination of a carboxylic acid. It actually connects over to another carbon. So that's your functional group there for an ester. And because it kind of looks like carboxylic acid, not surprising enough, it is made from a carboxylic acid and actually an alcohol coming together. Basically, squish them together. And esters are synthesized from the reaction of a carboxylic acid and an alcohol. This is what is known as an esterification reaction, which is the reaction that makes esters. So what happens is essentially we take our carboxylic acid and we could take an alcohol, such as any alcohol, really. If I get that, there you go. Plus an alcohol here. I'll just do this guy here. And as you might imagine, we're actually going to take out a couple of H's and an oxygen. So we're going to take out water, essentially. And water is going to go out. And then basically what we're going to do is just kind of squish both sides together. Basically, we're going to squish this guy together with that side. And again, nothing changes. So starting on the left there, copying everything exactly the same. I'm obviously going to pick back up over here as this is the ester connection. So that's always how you want to make sure you put it together through that connection right there. And that's going to give me this guy right here, which again is basically our ester connection happening in that case. So if your alcohol, for example, was turned around like we just did there, again, it's sometimes easier to sort of just turn the alcohol around like we did so you could line it up. But in this case, we would take this guy and this guy off, which obviously would still give us our water. But the importance is when we go put them together, if you don't rearrange it, you got to make sure you connect this way first and then to that guy as well. So again, sometimes if you kind of turn the alcohol around, it kind of puts it in the right orientation. You can take the water out and then just kind of push both sides together. But if you don't do that, or it's not written like that, make sure that you realize that again, you do not want to connect it this way into the carbon here, right? So you want to make sure you get it through the oxygen and make that ester bond. Esters are found in fats and oils. They're responsible for smells, flavors. Things like bananas, oranges, strawberries are all esters that come together. So once again, here is that esterification reaction. We're basically going to take a carboxylic acid. We're going to take an alcohol. We're just going to take out water, basically, and squish it all together. So once again, it is sometimes very helpful to kind of arrange your alcohol like you could just see the water coming. And if you do that, you're just left with copying on both sides of the box. Mix out the water, copy both sides around the box there and push them together. And again, that will get you your ester in this case. The ester, because it is basically named for a carboxylic acid and an alcohol, it has sort of two parts to it, and we'll talk about the name in just a second. But let's take a look at maybe, why don't you try one here? So why don't you try Okay, let's take a look. And again here, I got a carboxylic acid and an alcohol going to come together to make my ester in this esterification reaction. So since I know that, I should also know that really the way they're going to come together is really functional group to functional group. So again, just to easily visualize what's going on, I'm going to redraw my alcohol here heading in the other direction, kind of putting the functional group next to the other functional group. So we had 3 carbons, I believe, in this one, if I didn't screw it up there. So I'm just going to kind of turn around. And again, the reason I want to do that is just to make it easier for myself. I know I need to take water out. So at this point, what I could do is just simply put a box around water. And I know that's what's going to come out. And by kind of arranging it in this fashion, now really all I have to do is, like we talked about before, pretty much just copy what's there in that order and just basically put it together, and then that will get you to what you need. So if I do that, I'm just copying my left to right here. And again, I'm not changing anything. I'm just going to take out the water. I'm going to make sure I make my ester connection, which again is always to the oxygen there. And then we'll just continue copying on the right hand side there and try not to run out of room. We'll squeeze it in there at the end. And again, we'll get our ester in this particular case. Any questions on that? So again, you just want to kind of make it easier for yourself. And you want to make sure you don't do any kind of weird connection because maybe it's not facing in the right way for you. Any questions on that one there? All right, same deal here really. And I could leave this guy the way it is if I want to. I could actually just turn this guy around again, kind of getting functional group to functional group being near each other. So I'm just going to copy this guy and kind of turn him around. So I got 1, 2, 3, and 4 carbons there. And now again, I have it really set up the way I want it, where I could just box out the water and then just copy what's there, right? So we're going to box out our water. We're going to, in this particular case, it doesn't really truly matter where you box it out, but really, I guess it's more of that wrong box there. It'll come out the same, but so kind of turned around, doesn't really matter. Even if you messed up there and boxed out water like I did, it'll come out the same. You can just do it that way. And in this case, we're just going to copy, same deal, left to right, and just put everybody together. So we'll get this, we'll get this. We'll have our oxygen to here. We'll have that, 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 and that. And obviously we'll have some water that goes there. So the esterification reaction, not too bad. Basically just take out water squish everybody together. Make sure though, again, the connection is the ester connection and that you kind of put it together correctly. And like I said, kind of putting the two functional groups kind of back to back is sometimes really helpful in sort of visualizing what you need to put there. So you don't get any, incorrect sort of connection happening. So again, sometimes people will just end up like that and try to do some weird thing where they take that and before you know you'll get the wrong answer and stuff like that. Any questions on that there? All right, so why don't you do this one? Write the balanced chemical equation for the reaction of propanoic acid and methanol in the presence of heat and an acid catalyst. Again, propane going to tell us we got 3 carbons happening there. And again, we're going to fill in our hydrogens. And again, we have a carboxylic acid. Methanol, OL, tells us it's an alcohol. Methane means 1 carbon. And since I know I got a carboxylic acid and an alcohol coming together, I am going to kind of draw my alcohol again, sort of facing in the right direction there. So everything lines up nicely. We got some heat, which is sometimes abbreviated with a delta symbol, and an acid catalyst is sometimes abbreviated with an H plus on top of the arrow. It doesn't really matter for our purposes here, but if you see it, it's what it's for. It has really no effect on, kind of what we get at the end here. At this point, I know I got a carboxylic acid and alcohol. It should give me an ester. The heat also might tell you a little dehydration, right? So basically going to take out the water in this case. So we're going to take out our water. And again, at this point, since we lined it up nicely, we're just going to go left to right and squeeze everybody together. And that's going to get us here something that looks like this. Again, making that ester connection. Badly done oxygen there, put it together a little better. And again, we get our ester in this case. So again, carboxylic acid, alcohol, ester is the outcome. Any questions on that one? There they agree, so that's good. So let's talk about naming esters. So as we've seen, it's basically derived from an alcohol and a carboxylic acid coming together to make the ester through that esterification reaction. Again, usually an acid or some heat is used to do that. Again, anytime you see heat, a lot of times that involves some water being lost probably somewhere. So the naming, not surprisingly, is based off of those two things. So part of the name is based off the carboxylic acid name, bless you, and part of it is named off of the alcohol name. The alcohol we name as a group. So the part that comes from the alcohol would be named as a group, like a YL type of group, like a methyl, ethyl, propyl type group. And the carboxylic acid, however you want to remember it, you could take the oic acid off and put O8 at the end of it. So O8 goes at the end of that part. So to show you again, the one we just did, how do I know which part came from where? I know that how I put this together, right, is as we just did, basically right here. And going to the carbon double bonded oxygen and going in that direction, that part comes from the carboxylic acid. So that's what you want to count up for your main part of the name. In this case is 3, based off obviously of this guy. So this is propano 8. It gets the O8 at the end of it. The going away from the double bond, that's always going to get you the alcohol part, and that's where the other part of the name comes from. And this particular one, there's just 1 carbon, which is a methyl group, and this would be known as methyl propanoate. And again, the back name there from the carboxylic acid part and the basically alcohol parts named like a group. So if we look at the one here in this example, which might be a little different, it is. So when we look at this, once again, I would always sort of go to where the connection happens. And obviously, we basically put it together right there, right between the carbon and the oxygen. And once again, heading towards the double bond, that's your carboxylic acid part. Heading away from the double bond is your alcohol part, right? So that will give us our names we need. Carboxylic acid, the main part of the name too, which is based off of ethane. So this is ethanoate, right? O8 at the end of it. And this also has a one carbon on the alcohol. So a little methyl ethanoate. Any questions on that one there? So with an ester, that's sort of where I would kind of go to. If you have the ester and you want to name it, kind of break it there, put a line there between the carbon and the oxygen. And again, going whichever way the double bond's located, going that way will get you. And I say it won't always be to the left because we could have obviously had it drawn like this, right? Right there, just one more, I think. So again, if you still do that and always go towards the double bond, that's always going to get you the carboxylic acid part, yeah. And then obviously go in the other direction for the alcohol. So no matter which way it's sort of oriented, we'll always go in that sort of direction correctly. Any questions on that there? All right, so esters do have common names. We have ethyl ethanoate, which is ethyl acetate, methyl propanoate. And again, how we get these names, once again, coming here, going towards the carboxylic acid part of double bond, 2 carbons, ethanoate, going the other way to our alcohol, which gets named as a group. So ethyl ethanoate in that case. Same thing here, breaking here, going towards the carbon oxygen double bond to get my main part of the name. 1, 2, 3 carbons, propanoate, going away from the double bond to get my group name, which is this 1 carbon, and again, methyl. And same thing here, we'll go right about there, going towards my double bond. That is benzoic acid, right? So that's how we get to benzoate, right? That's the benzene ring there. And again, going away from it, 2 carbons, ethyl. Any questions on that one there? All right. Salicylic acid is also an ester. As you can see here, we have a carboxylic acid happening and also our alcohol part here, and they're going to come together. And this is our ester connection right there. Again, that is from our carboxylic acid. And that way is really from our alcohol in this case. And that is basically the main component basically of aspirin, basically right there. Oil wintergreen, our methyl salicylate is a pungent odor, minty, sort of fresh, if you will. It's used in skin ointments and can't pass through the skin. Same deal, same sort of connection sort of happening here. Carboxylic acid part and alcohol part coming together, connecting right there in that particular case. All right, so why don't you name this one? Why don't you name this one? Why don't you name why don't you name that one? Why don't you draw? Let's do about let's do pentyl hexanoate. I want you to draw ethyl butanoate. Yeah, let's take a look at some of these here. Again, you should hopefully recognize this as our ester group. And if you do see this again as the ester group, you need to name it. Again, recommend just, just putting like a little line there between the carbon and the oxygen. And then remembering pretty much the main part of the name is going to come from where the carbon oxygen double bond is, as that is your carboxylic acid part. So that is where you want to start, 1, 2, and 3. That is based off of propane because it is a ester. It's going to get the O8 ending at the bottom of it or at the end of it. Going the other way will give you your alcohol, which is just named as a group. So that is a 2-carbon group there. So again, that is ethyl propanoate. Any questions on that one? Here in line structure, remember this is a carbon, so basically right there is your ester group, basically. You could do the exact same thing, just kind of throw up a line right there between the carbon and the oxygen. Always head towards the carbon-oxygen double bond for the main part of the name, and you want to count up carbons. You don't want to forget this carbon, though, so that is 1 carbon, that is 2 carbons, 3 carbons, and again here 4 carbons. So that is going to be butanoate. Going in the other direction where the single bonded oxygen is going to be our alcohol, counting up carbons 1, 2, and 3. So that's going to be a propyl butanoate. Any questions on that one there? Same thing here, ester group right about there, line between the carbon and the oxygen, go towards the double bond for the main part of the name. So 1, 2, and 3. So again, that's going to give us a propanoate at the end. Going the other direction for our group, 1, 2, 3, 4. That's based off of butane, and that would be a butyl group, right? So butyl propanoate. Any questions on any of the names there? Drawing, we're not going to do anything different. Maybe slightly different, but really not too much than we've done before. We're going to work backwards. So really the first thing that we see is O8, and that tells us it's an ester. So because we know kind of the ester group has to kind of go in the middle of the molecule because it's basically the 2 parts coming together, I actually, in this case, would actually start with just the functional group there in the middle. Is a good way to do it. So I'm going to lay myself up somewhere. I'm not sure. I'll get rid of something here so I could maybe draw it. I'll get rid of this here. So because I know that group really is sort of in the middle of the molecule, that's actually what I'm going to start with. And I'm just going to draw my sort of ester group here. And now what I want to do then is go with the hexane, which is 6 carbons. And that is from the carboxylic acid part, which in my case would be going in this direction, right? Because that's where my double bond is. Again, if you drew your carboxylic acid or your ester group this way, your carboxylic acid would be going in that direction, right? So it doesn't really matter which way you want to kind of draw your functional group to do that. I'm actually going to move them both over because I think I'm going to run out of room there on the left. So I'm just going to move it over to give me a little bit more room. All right, so I'm going to draw my ester group to start with. And we're just going to kind of do this move here. And again, going this way with my double bonded oxygen is going to be my hexane part of it, which is 6 carbons. The other thing you do need to remember is you already got a carbon, right? So I actually just need to add 5 carbons there to give me a total of 6. You don't want to add 6 more. Otherwise, you'll have 7. So that's 3, 4, 5, and 6 at that point. That basically takes care of that. Going the other way is my group, which is pentyl, and that's 5 carbons. Once again, you need to remember that should be a note right there. We're going to go to the opposite side here. 1, 2, 3, 4, and 5. And then everything else is hydrogen. So we'll put a hydrogen there. We'll need 2 there. We'll need 2 there. 2, 2. This guy doesn't need any. 2, 2, 2, 2, and 3 in that case. Any questions on that one there? Same thing here. O8 tells us it's an ester. Butane tells us our carboxylic acid basically has 4 carbons. So I'm going to start once again with my ester group here. And because I drew it this way, that is my carboxylic acid side to the left. And I need 4. I already got 1. So that's going to be 2, 3, and 4. And ethyl on the other side is going to be 2. And now we're ready to put in our hydrogens. So proper number of hydrogens to get to 4. And we should hopefully be in business at that point. Any question on that one? So with this one, you might want to start with what's in the middle because that's sort of where the group's going to end up, and just kind of build out to the left and the right of it. Sometimes more easy to kind of line everything up. Any questions on that there? Your ester group here. Again, once I see the ester group, I know when I want to go name, I'm just going to put a line right there between the carbon, the oxygen, single bonded, and head towards the double bonded oxygen, as that will give me the base of my name, which is 2 carbons. So again, that's going to be an ethanoate. Going the other way where my single bonded guy is going to give me my group name or alcohol, which is 3. And again, this is going to give us propyl ethanoate in this case. So, any questions on that one there? So as we've been talking about, esters are really responsible for a lot of fragrances and also sort of flavors as well. A lot of perfumes and stuff. Esters can be volatile, so they do give off obviously odors. Volatile means something can go in the gas phase really easily. And again, that's going to obviously allow you to smell different sort of smells, which you might be doing in the lab this week. So pears, for example, here's propyl ethanoate, the one we just did. Again, we would break here, carboxylic acid, alcohol. Bananas here, pentyl ethanoate, also breaking here, alcohol part, our pentyl part, and our ethanoate part there. Breaking right here, octyl ethanoate for oranges, long 8 carbons going that way for our octyl group, 2 carbons for our base. And then obviously here we would break right there. And that is 4 carbons for butanoate, 2 carbons for ethyl for pineapples. And lastly here for some apricots, 4 carbons that way, which is our butanoate. And again, a 5-pack of carbons heading in the other direction there for our pentyl group in that particular case there. All right, draw a couple here, see what you come up with. 3-bromobutanoic acid. All right, let's take a look. Again, we want to identify what we're dealing with. So going backwards, oic acid tells us it's actually a carboxylic acid, right, on this one? And butanoic acid tells us it's 4 carbons, so that's what we'll start with. And it does have a carboxylic acid group, and once again, you can put it on the left-hand side, right-hand side. It is your call. I'm going to go right-hand side here. So that basically will take care of that part of the name. 3-bromo means I have a bromine, a carbon number 3. Remember, because I kind of put my group to the right, that for me has to be carbon number 1, which means for me, carbon number 3 would be right about there. Obviously, if you put it on the other side, you'd be going the other direction there. At that point, we're nothing left but hydrogens. So a couple there, maybe 1 there, and 3 in that case there. Any questions on that there? And obviously that's just a number, so no line or anything like that. All right, coming here, 08 tells us it's an ester. And that also tells me that's probably where I should kind of start my connection. So I'm just going to kind of draw my ester connection at this point. Now I just got to dissect my name correctly. So propane comes from the carboxylic acid side. And I know the carboxylic acid side is always towards the double bonded oxygen. So I got to go that way. I do need to remember I already got a carbon down 1 here. So we don't want to put 3 carbons in addition to that one. We want a total of 3 carbons, and that will get us there. That's going to take care of all that. Now going the other way is really the alcohol part, which is what the group is for. And ethyl is 2 carbons based off of ethane. And at this point, we could just fill in our hydrogens as well. again to get to 4 and maybe 2 there and a 3-pack right there. Any questions on any of those drawings there? Yeah. On which one are we talking about? I'm sorry. On B? And you're asking we don't put the number in front, like why there's no number here in front of ethyl? Yeah, we don't because it's really based by putting those two things together, and it does come from the alcohol. So it's not really it's not a group that's attached to a carbon, and that's typically what the numbers are for. So when you look at this group, it's really not attached to a carbon, it's actually attached to the oxygen, and that's why there's no numbers. So usually the numbers are reserved for any groups that are attached to like carbons and stuff like that. Yeah. Other questions? Probably. All right, let's see here. Let's talk about some reactions that esters undergo. Hydrolysis reaction is one that they do. So hydrolysis, right, involves water. So it's kind of like putting water back in, if you will. And how we make an ester is we take water out. So one way we could kind of break it back apart is to kind of put the water back in and it'll break back apart. Now, when we do this, there's two types of hydrolysis reactions. One is an acid hydrolysis and one is a base hydrolysis. In an acid hydrolysis, we take our ester, and maybe no surprise here, but we're going to add water in this case. And you will see H plus, and that's the acid as a catalyst and heat involved in this case. So what's going to happen in this case is we're basically, this reaction here is the opposite of the esterification reaction where we put it together. So this is basically the exact opposite of it. And that means the way we put it together is we know we kind of put it together right about here. So what's going to happen in this case is it's actually just going to break apart right in that exact same spot. So what you would probably want to do in this case is just draw the two halves, basically broken apart. So if I were to do this, I would copy my guy on the left there, and I'm going to break it apart. And then I would copy my guy to the right and broken apart. And these are really the two parts that are going to receive these two guys. And basically, we know this guy is our carboxylic acid, right? And this guy is our alcohol. So if we think about it, we just need to put in there what they're missing to make them those things, right? So this guy is missing the OH, right, to become a carboxylic acid again. So that is where the OH ends up. And this guy here is missing just a hydrogen to become an alcohol. So that guy's going to go here. And now we get back basically our alcohol and our carboxylic acid. So you could think of the acid hydrolysis of an ester as basically the reverse reaction to putting it together. You're just going to break it apart. You're going to break it apart in the same place it comes together. And you're going to kind of just put the water back in that particular case. Any questions on that there? Now, the base hydrolysis is a little different. And because it's basic, there's not as much H plus floating around to actually allow you to get back everything that you need. So you're going to be kind of short some hydrogens because it's not basic. It's not acidic like the previous one where it's acidic, has a lot of H pluses floating around. It's more basic in this case. It still really sort of works the same way. So for example, if you take your ester, and once again, in this case, we're actually going to add sodium hydroxide here. Kind of like this. And again, there'll be some heat involved. So we are going to break it apart right here. And we'll get our two halves, basically. And we'll have this over here. Now, the difference is we actually will not, because it's basic, we will not get the carboxylic acid back because frankly, it's basic. And that hydrogen you want to put back on there is not going to stay on because it's basic. It's going to come off basically and make water. So we actually do get the alcohol back. So we will get our alcohol back just the way it is. And that is basically what's going to happen in this case. What's left is really an oxygen and a sodium, and that will actually find its way over here. It's really a salt in this case, and we will get the salt that basically will occur. So we do not get the carboxylic acid back. We actually get a carboxylic acid salt that basically develops here because it's basic in this case. This is what is sometimes referred to as a saponification reaction. It's basically how soap is made, basically. Yeah. So you take a long chain fatty acid and you basically do this reaction with it, and you get basically soap, which is just a long old carbon hydrogen chain that basically has like the ester group at the end of it. And that is basically what soap is. These are all carbons, hydrogens here. And soap has a nonpolar part, which is sometimes referred to as the nonpolar tail of soap. This part up here is the polar part of soap, or the polar head. And that works really well, for example, when you are dealing with soap, because dirt is actually nonpolar. And the nonpolar part of soap will basically trap the dirt in what's known as a micelle, basically. It'll get that nonpolar part because like dissolves like. So nonpolar mix really well together. What that also does is it keeps the polar part on the outside. And that's really good because typically speaking, when you use soap, you usually do what after you put soap on? You usually put a little bit of water on there to wash it off. So when you go and use your water, which is polar, now you got like dissolves like on the outside, and it will go and grab all those guys and the dirt that's trapped, and off it goes, right? And you're clean, and off goes the dirt, and it works really well. So soap having kind of a non-polar part works well with the dirt part, and the polar part of soap works really well with water to kind of wash it off and keep it all trapped and stuff like that. So this sort of base hydrolysis or saponification reaction where you use a strong base is usually basically what's done in that situation. So in the acid hydrolysis, we do get back both parts exactly the way it started. But with the base one, because it's really done with a strong base, we can't get the carboxylic acid part back. So a good way to remember that, right, is you got a base, you can't get the acid back, right? So if you're reacting with a base, you won't get the acid back, but you will get the alcohol back in both situations in this case. Any questions on that? So why don't you try it? Why don't you draw what you would get if you started with methyl ethanoate in both cases, doing water and an acid catalyst, and potassium hydroxide, which is a strong base on the bottom. Okay, let's take a look and see. We'll start with ethanoate. So O8 tells us obviously it is a ester. So we'll start with our ester connection here. And again, ethanoate is 2 carbons on the carboxylic acid side. So it'll look something like this. And methyl is a 1 carbon on the alcohol side. So that should be kind of what we're starting with in this case. First one, we're going to add some water and a little acid hydrolysis here. So a little bit of that. So once again, as we talked about, we are just going to basically break this guy apart. We'll start with the 2 components here. So we end up with this guy, and then we'll end up with basically this guy here. So remember, in this case, with the acid, we are going to get basically back everything the way we need it. So we will get our carboxylic acid, which is the OH needs to go over there. And again, to make this guy into a alcohol, we need an H that will end up there. And that'll get us back our carboxylic acid and our alcohol. Any questions on that one there? Bottom one, we're starting with the same thing. Actually, I'll just draw a little bit higher here. Let's go above it, I think. Different here, though, we are adding KOH, which is, again, a strong base. So remember, in this case, we're still going to break it apart here. We're still just going to draw the parts to it. We just got to make sure we kind of build it correctly here at the end, and we'll end up with this. In both cases, we always get the alcohol back. So he's going to get the hydrogen. If you just want to keep accounting of everything, that means that's gone, right? So that leaves us basically an oxygen and a potassium in this case. And we know the ester sort of connection is the oxygen, so that's got to go there. And that's going to be a negative, and really the potassium there is going to hang out as a salt in this case. Again, we're not going to get the carboxylic acid. We're going to get more of a carboxylic acid salt back in this particular case because it is basic. Any questions on that one there? Ah, there it is. All right, we are off to amines now because, we only got like 2 more organic groups to go. So this would be one of it. It is nitrogen time here. So nitrogen here is an amine. The functional group of amines are, like I said, nitrogen based. They are an NH2 here. They are really derivatives of ammonia. So they're kind of like ammonia based. So they're kind of very much sort of derivatives of ammonia in this particular case. So they do contain a nitrogen, as you can see here, nitrogen, hydrogen. That's our amine group in this case. So amines, as I mentioned, are derivatives of ammonia. And they do have really the non-bonding electrons. And typically speaking, though, they also will have one less hydrogen than ammonia to start with, because again, it would have too many bonds, obviously, if it was NH3 and you put a bond on it. So that's usually why it's NH2. And here are some examples of amines. We have a nitrogen here, and it's contained there, a nitrogen as well, and a nitrogen here. Now, our amines, just like we could do with carbons, just like we could do with alcohols, we do have primary, secondary, and tertiary amines. Why not, right? So why would we have that? Well, in this case, we're going to be looking at the nitrogen, and we do basically the same thing. We want to look at the nitrogen, and we actually want to see how many carbons are directly attached to the nitrogen. So if you look at this guy, that nitrogen has basically 3 carbons attached directly to it. That would be a tertiary amine in this case. That's also, by the way, why that nitrogen has no hydrogens attached to it, right? Because it's all taken up with the carbons. This nitrogen has how many carbons attached to it? It actually has just 1 right about there. Yeah, so that's the carbon. Those are hydrogens on the other side. And this would be a primary amine in that case because it has 1 carbon attached. And here, this guy has 1 and 2. This would be a secondary amine. So very similar to what we do, except in this case, it's the nitrogen that's the important one. And we're looking at how many carbons are directly attached to the nitrogens for primary, secondary, tertiary. You could do the same thing. And again, sometimes people teach you to do it with the hydrogens. But again, I like just counting the carbons because it just tells you the correct number. So there's 1 carbon as primary versus there's 2 hydrogens as primary. So that's a good way to do it. So as we can see there, our primary, secondary, tertiary. As we continue to add carbons, we do lose hydrogens. And as you can see there, our tertiary amine has no hydrogens attached. Now, the way we're going to sort of name amines is we're going to go more of a common name way. Why not? And basically, common name way is we go to the nitrogen and we basically just find what groups are attached to it. Very similar to how we name ethers, right? When we had those ethers, we had the oxygens, right? We had the oxygen in the middle, and we had some groups on either side of it. And this would be dimethyl ether. So we're going to name amines similar to that. We're going to go more of the common route than the IUPAC way. And here, this is a nitrogen that has basically a methyl group attached. So that is methylamine, and just put amine at the end of it. This nitrogen has 2 methyl groups attached. So that is dimethyl, and just put amine at the end of it. And for the trifecta here, we got 1, 2, and 3 methyl groups attached. That's going to be trimethylamine. And again, we'll kind of go that sort of route in terms of naming. So for simple amines, we'll go with that type of naming. We just kind of name the groups. The groups would obviously be in alphabetical order like normal. You do not need to necessarily give the location of where those groups are. You could just tell it basically alphabetically what's there. So here we have basically ethylamine. Here we have dimethylamine. And here we have an ethyl group and 2 methyls. So that's ethyl dimethylamine. A reminder that when we have a prefix, we ignore the prefix in alphabetical. So that's why the di comes second. M after E is basically what we're looking at in this particular case. All right, so write the common name for these guys. Also classify them as primary, secondary, tertiary. Why don't you also draw? You also draw something. Let's do ethyl propylamine. And why don't you do diethylamine? Okay, let's take a look here. So this is definitely an amine. And by the way, again, just like ammonia, that nitrogen does have actually never usually drawn too much, those 2 non-bonding electrons on the nitrogen. And that's really how it gets to 8 for the octet rule. It's got the 2 hydrogens, the 1 bond to the carbon, and the 2 non-bonding electrons gives it its 8 electrons. So that's what we got going on there. Since that's an amine, we have this guy really as just a group. So that is going to be ethylamine. In this case. Here we can look at the nitrogen, and here we have a methyl group and another methyl group. So that is a dimethyl group there with our nitrogen. That is a 2-carbon group, which is an ethyl group. And again, putting this in alphabetical order, we will actually go with the E first because we're doing the E to the M, and that's going to be an ethyl dimethyl amine in this case. Yeah. Any question on those? Yeah. It probably would because there's 3 of them. I would agree with you. Propylamine, just making sure you're paying attention out there. Yes, thank you very much. It actually is 3 carbons. That would be much better. Other questions on that there? All right. So obviously count the right number of carbons. I think I counted them wrong. I just hit the wrong name. To just illustrate, there was a question earlier about, for example, with the group that was attached to the oxygen, why there's no numbers. Sometimes with amines and amides, which are nitrogen-containing groups, sometimes you will see some names where they will actually use N in place of numbers. And the reason they use N is because the groups are technically attached to the nitrogens. So for example here, if you're going to take another approach to this name, which is not necessarily a common name approach, what you would actually do is what we normally do, which is try to find the longest carbon chain that's attached to the nitrogen. And in this case, it would actually be the guy on the left there, which would be ethyl. And that would be kind of the base of your name, like ethane amine. And now what you would do with these groups that are attached is they are attached to the nitrogen and they're not attached to a carbon, so they won't actually get a number. And they would actually be like N comma N, kind of like when you give 2 numbers. And this would be dimethyl ethane amine. And that is another way that sometimes amines are named, and sometimes you will see these ends pop up. And really, what the ends mean is basically the groups are attached to the nitrogen. They're not attached to like the longest carbon chain or anything like that. So, as we were talking about earlier with that other question, again, typically numbers are reserved for groups that are attached to sort of carbons. And so, for some other things, they sometimes use some different sort of ways to name them. But for us, you won't have to worry about kind of rolling that way. We will go with obviously the common name here for our amines. Question.
Yep. Um,
There's two ends because there's actually two methyls on the nitrogen, two different ones. So just like, for example, if you had like a carbon, right, and you had a methyl group on this guy, right, and a methyl group on this guy, and they say this is carbon one, you would go 1, 1, right? Dimethyl. It's basically the same sort of idea as that, yeah. And if you just had one group, for example, just say we had this and then maybe just this, and then this is an H. This guy would actually just get one end, and it'd be N-methyl just because there's one. So it's very similar to using numbers. And again, if there's two of them on there, you would use the N like twice and stuff like that. Yeah. Other questions? And that sometimes happens in some books and places. Sometimes people will name secondary and tertiary amines that way. And so if you happen to come across it, that's basically what those ends mean. It's basically those groups are attached to the nitrogen in those things. Primary ones, you typically don't see that because again, there's really no group attached to it. Kind of the longest carbon chain is just attached to like the first one. Other questions on that? Okay, so let's draw a couple here to see. So amine means it's a nitrogen, and so kind of like how we talked about drawing ethers, I would probably also take that approach here with our amines. So like with our ethers, we start with the oxygen, kind of put the groups on the either side of it. Here I would start with the nitrogen and just add your groups as needed. So propyl is a 3-carbon group. It doesn't really matter which side you put it on. So you can put it on the left or the right in this case. And ethyl is a 2-carbon group. And just like normal, we're just going to fill in our hydrogens on our carbons. But we do have a little bit of work to still do with our nitrogen because technically speaking, it does have the dots, right? Which means that nitrogen has how many electrons right now? It has only 6, right? So it actually will need a hydrogen attached to it as well to sort of complete it out. So that's what I was talking about earlier when I was mentioning, they really do have those 2 dots. So you kind of still want to get nitrogen here to 4. I won't say bonds, but you want 4 sort of things there, basically 8 electrons. So you do also want to kind of fill the nitrogen in with the appropriate number of hydrogens if necessary. And as you can see here with our tertiary, there is no hydrogens on a tertiary, again, because it does have those dots that gets it to 8. So with an extra hydrogen, you have too many electrons on that nitrogen. Here, amine and then diethyl. So once again, going to start with the nitrogen. Diethyl means I got an ethyl group going in both directions. So we'll just kind of fill that in. We'll fill that in. And once again, we will need a hydrogen there. You don't necessarily have to draw it, but again, it has the dots that are basically there as well to complete it out. Yes. If it's the whole thing's turned, it's perfectly fine. Yeah, it don't matter which one. It don't matter where you put it. Frankly speaking, you could have put one going up too if you wanted to. It doesn't really matter. Yeah. So as long as you're again, obviously on a different sort of size of the nitrogen, it's okay. Other questions? So we also saw basically an amine with a benzene ring earlier when we were talking about benzene. Remember, if you have this NH2 here with a benzene ring, that whole thing is known as sort of that traditional name of aniline. And again, we would call that carbon number 1 where that nitrogen group is attached, 2, 3, and 4 for our bromo group. So 4-bromoaniline. So as I was talking about a second ago, you can see here on the last one, we do have aniline, which is still this whole thing basically. But different than this one, where the group is attached to a carbon, and because this group is attached to a carbon, we have a number, we actually have a methyl group. And it is not attached to a carbon, but it is attached to the nitrogen, as we were just talking about. So that is where the N comes from, again, telling you that the methyl group is attached to the nitrogen. And again, the aniline is still basically the whole benzene ring with that. So again, like I said, sometimes with secondary and tertiary amines and amides as well, you'll sometimes see those N's pop into some of the names and stuff like that. So it's straightforward. You just got to remember N is nitrogen. So that is where the groups basically are attached. Any questions on that there? All right. So why don't you get the common names for each of these and see what you come. Okay, so let's take a look. Let's first start with this. This is obviously an amine, as we have a nitrogen. That is a primary, secondary, tertiary. That is a tertiary, as again, it's attached to 1, 2, and 3 carbons. We're going to go common name here. So I see a methyl group there. I see an ethyl group there. And I see one more ethyl group over there. So that's 2 ethyls in there. So that's a diethyl, right? And then we have a methyl, and then we have an amine. Yeah, so diethyl methyl amine. Any questions on that one? This is aniline, right? Right, that whole thing. And here we do actually have a group attached, which is an ethyl group. But in this particular case, once again, here it is not attached to a carbon in the ring. It is actually attached to the nitrogen. So this would be an N-ethyl aniline, right? This guy. So any questions on that one there? Yeah.
The first one, I did I don't also have to try, so it's.
Yeah, there actually is there's only one methyl group. So it's only this one is a methyl group. These are methyl groups because these are all together. So this whole thing is an ethyl group. And that CH3 at the end of that one is also part of the ethyl group. So there's actually only one methyl group actually in this particular case. Yeah. So the ethyl is a 2 carbon group, and that CH3 at the ends, which I'm assuming is where you got the tri from, are part of that ethyl group. Yeah. Yep. Other questions? All right. I think we will lay it up there for